Hello everyone. My name is Prashant and I'm a postdoc in Bar-Ilan University. So today I'll talk about some trapping aspects of a Sokoban random walk. I'll explain the model. And this is a joint work with Eli Burkai and David Kessler, both of whom are also from Bar-Ilan University. So random walks are commonly studied in statistical physics, and one of the simplest models is that of a classical Markovian random walk, which is evolving in discrete space and discrete time in 2 dimension. And at a time step, it can jump to one of its neighboring sites with equal probability. At large times, the typical fluctuations of the position for this model are described by Gaussian probability distribution with mean square displacement that grows linearly in time. Another well-studied model, particularly in the context of percolation, is the ant in a labyrinth model introduced by Jain in 1976. So this model features a random walk which is moving in 2 dimensions, but it's moving in a disordered environment that contains obstacles. So we put initially the walker at the origin, but every other site can have an obstacle with probability rho, or it can remain empty with the complementary probability 1 minus rho. And the walker, just like the previous case, can choose one of its neighboring sites with equal probability and attempt a jump. But the jump is successful only if this neighboring site is free of obstacle. Like here, if it is already occupied with some obstacle, so the jump is not successful. Note that this represents a quench disorder scenario where the configuration of the obstacles varies from realization to realization, but for a given realization, the obstacles are static. Yeah, so this particular model exhibits what is known as the percolation transition. So if you have very high densities of obstacles, the walker will be confined here and it won't escape to the infinity. But as you decrease the density of the obstacles at low enough densities, there will be some paths of vacant sites which can lead the walker to infinity. So there will be some percolation. And this transition from percolation to no percolation in 2 dimensions happen in this critical density. One of the signatures to see this is via the MSD as a function of time. So for rho greater than rho c, the MSD saturates to some finite value, whereas at or below the threshold, the MSD doesn't saturate, it keeps on increasing. One another quantity which is quite studied in the context of the AIL model is the notion of trapping. So the scenario is just like the previous case, but the walker is killed once it encounters an obstacle. The moment it touches an obstacle, it gets killed. So the question is, what is the probability that up to time n, the walker has survived? Note that this probability will depend on the stochastic motion of the walker, but it will also depend on the configuration because that itself is random. And there has been several studies in this direction, and what they found is that the long time decay of the survival probability in d dimension has this stretched exponential form as shown here. The beta is a dimension dependent constant term and lambda depends on the density in this way. We will refer to this formula as the BVDV formula, named after Balagurov, Vax, Donskar, and Varadan. At d equal to 1, the stretch exponent is 1 by 3, and at d equal to 2, it's half, and so on. So recently, Bonomo and Ruveni in 2023 introduced a further variant of this AIL model, and they called it the Sokoban random walk. And this, again, is a walker moving in a disordered environment with containing obstacles. But unlike the previous case, the walker is capable of locally modifying its environment. So the dynamics is the following. If the neighboring site is already free of obstacle, then the Sokoban can jump. If this neighboring site is occupied by an obstacle, but the next neighboring site is free, the Sokoban can still move by pushing this obstacle here. However, there's limit on this pushing capacity in the sense that if two obstacles are together, the walker cannot push. So intuitively, one would, from naive intuition, anticipate that if introducing this pushing should enhance the escape of the walker because, the walker should be able to carve out its path through the obstacles. But surprisingly, what simulations from this paper showed was that even at low obstacle densities at which AIL is not confined, the Sokoban is confined by the obstacles. And they studied this by using MSD as a function of time. And even at densities which are below the percolation threshold, like 0.4, 0.37, the claim is that the MSD saturates if you go to large enough time. So we were interested in this model due to the following questions. Firstly, can we physically better understand the low to moderate density physics of a Sokoban, because pushing seems to be doing something which is giving a different transport behavior. So can we physically understand that? Second is the pushing induces some confined state, but how does the walker dynamically relax towards this confined state? Thirdly, are there some characteristic densities or exponents for the Sokoban model, because the percolation exponents, percolation threshold are not there. So are there some characteristic exponential densities? And the final question is, how generic are these properties, in the sense that if you modify the microscopic pushing rules, do these features remain robust under those changes? So to answer these questions, we looked at the number of distinct sites visited by Sokoban as a function of time. This is a non-negative function of time. It's plotted here. It can either remain constant or increase by 1 unit. And if the walker gets confined, then this should saturate to some finite value at the large time limit. So this end time where the first, saturated value has been attained for the first time, we call it caging time. Second, we look at the survival probability that the Sokoban is not caged up to time n. And finally, once it gets caged, what is the size of that cage? So in one dimension, we showed that the Sokoban, the survival probability that it has not been caged has this kind of stretched exponential form. And I would like to recall the BDVD formula that we have for the classical problem. And here we see that the exponents, the stretched exponential exponents are exactly the same for both models. This is the numerical verification of that. Now we considered a generalization where the Sokoban is capable of pushing up to n obstacles. Note that for the original model, n was equal to 1, but it can now push an arbitrary number of particles. And for large time and large n, capital N, we could do some large deviation to calculation to show that this particular form that we had in the previous slide, it's completely robust against n. And these are some of the verification of this formula with respect to simulation. So we see that in 1D, the Sokoban survival probability of not getting caged is completely universal, and it belongs to the BVDV universality class. Now, what happens in 2 dimensions? In 2 dimensions, analytical treatment is difficult, so we run many simulations of Sokoban, and even here, through a fitting procedure, we see that it's possible to fit this particular formula with some F-rho, which we numerically estimate. We also considered a modified Sokoban where the microscopic rules are different, but again, this form seems to describe the simulation data quite well. So even in 2 dimensions, for both Sokoban and its variant, we can fit this stretch exponent half to the data. So next, we looked at the average trap size as a function of time. So for AIL, this should diverge at the percolation threshold. But for the Sokoban, we see that it's a non-monotonic function of time. And this change happens at this density rho star, which is equal to 0.55. This turnover happens because the Sokoban, even though there might not be a cage at the initial time, but it can enter this region and it can modify this region into a cage like this. So that's why, and this happens especially at moderate to low densities. And that's why there's some self-trapping mechanism here that gives rise to this turnover, whereas here that self-trapping might not be as effective as in moderate densities. So this marks a crossover in the underlying trapping mechanism. Okay, so there were a bunch of questions that we were trying to understand. Can we physically better understand the low to moderate density physics? And the answer is limited pushing seems to induce, not seems, but it induces a trapping mechanism for rho less than rho star and the Sokoban cages itself. Plus, these were some of the other questions, and these are the answers. So I'll stop here.
Does this occur for all rho less than rho star?
Sorry?
This self-trapping, does it occur for all rho and very small for rho less than rho star?
If rho is very smaller than rho star, no, we couldn't do simulations beyond this. Like when, so till here we see that, but it's not obvious whether it will extend beyond this regime or not.
So like the earlier simulation, it seemed to show that the MSD saturates at some value, which increases with
Yeah.
decreasing density.
Yeah.
But now I guess you're saying that it's
Yeah, but now
eventually-
we are, so this is like time averaged MSD. So once it, yeah, once it enters this cage, so the size of, so ensemble average MSD would give you an idea about the overall extent, right? But this is more like once it cages, so what's the size of the trap? Yeah.
Maybe.
Say again, I didn't hear. Yeah. Yeah. No, it can push only one obstacle is there. If there are already many obstacles, it cannot push. So there's finiteness in the pushing capacity, and so this model considered a most simple case where it can only push one obstacle. So if you have two obstacles like this, like it cannot push. It's half, same. Yeah, they are the same.
So, very nice talk. I had a question. Can you go back a few slides where a little bit more? Yeah, this one. No, yeah. So, when you did this, what is the size of the lattice you had taken? For example, if you had taken a bigger box, would what appears as a saturation, would it have gone up higher again?
No, these results are for infinite lattice. The two-dimensional lattice is of infinite extent, and you have these obstacles randomly thrown.
Oh, this is a infinite box.
Yeah,
like
it's in infinite
you have.
domain.
So that is it. Okay, and there is a second question, if you don't mind, that when the particle is pushing an obstacle, and whether it is one or later on you generalize to several, once it pushes, does it die there?
It doesn't.
So you
yeah.
said once that.
Yeah, here for instance, it will so keep on pushing it randomly as long as it attempts motion in that direction, but it can push it till the moment you get this kind of configuration.
Yes.
So beyond this, it cannot push.
All right, thank you.
I think we can thank the speaker.